Hi, everyone. Thank you for joining us today. You've probably been walking all over Vegas and going to different sessions. So please sit back and relax as we go from 0 to 100 million records per second. People there on the back don't relax so much. We don't want you to fall asleep. So today, instead of lecturing about how the metering system works in AWS, I have an idea. What we can do is something different. We will build a data processing system together with you. My name is Diego Macadar, and I'm here with Michael Ford. We are part of the metering and build generation team within the Commerce platform in AWS. The metering team basically collects all the usage that you use daily in AWS through all the services, and we aggregate that information and start the billing process from there. So many of you probably back in your offices build and maintain data processing systems. And we know from our own experience that dealing with data can be really difficult, especially when this data is growing all the time. So to build this architecture with you, we will explore some tools and techniques to deal with exponential growth of data. We will go through this with you together. For this architecture today, we will use a real example here for Las Vegas. Let's solve a real problem. So as you can see, there's many lights in Vegas. All the hotels and casinos and stadiums have lights all over. From some research, there's 15,000 miles of neon lights in Vegas. And only in Fremont Street, you can find 12 million light bulbs. So the problem that we want to solve today, it's by using smart socket technology, we want to gather the information of the lights and build a system to analyze what's going on there and provide orders for those lights so those get provisioned. So the information will flow from the smart sockets into our system and will generate aggregated information into the ordering systems. So these will basically improve the overall lighting experience in Vegas and also will reduce the cost and logistics of it. One thing that we need to consider here is that there's many lights in Vegas, and we need to make sure that we're not over-provisioning or under-provisioning these lights. If we over-provision the lights, what happens is that we will need to store those lights and really have a complex logistic model in order to send them to the right places. If we under-provision the lights, all the nice signs that you see all over Vegas will have black spots in it. So that takes me to the next thing, which is having 3 principles for this architecture. The number 1 will be that we need to be 100% accurate. We don't want to remember to under-provision or over-provision lights. And in order to do this, we need to have once and only once guarantee, meaning that any message that we get from the light sockets will be processed only once. It will not be duplicated or dropped. And another thing that we would want to accomplish in this architecture is that we want idempotent processing, meaning that any message that we get from these light sockets will be processed the same way anytime that we process the message. Another thing, there's always new casinos, new hotels opening here, so we want to be horizontally scalable. We want to have loosely coupled components so we can grow any of these components without having to impact the whole system. And of course, we want elasticity. We don't want to actually be operating these systems and having to be operationally working on that. So that takes me to the third part. That is basically that we want to focus on the business. We want to focus on the business and not having to context switch between operations and development. We want to make sure that this business is actually the one that we are focusing on. So we want to be operationally excellent. In AWS, we have a culture of operational excellence, and we want to use managed frameworks for this. So something that we will do today is we will explore these tools and techniques in detail on how we can improve the usage of that in order to grow this data from 0 to 100 million records per second. So now that we have the idea, let's start to define this architecture. And by defining this architecture, I will basically show what components we will be working with. We will start collecting the information from the light bulbs into our system. Then we will transform this information. If you think about these smart sockets will be basically metering the information that it's being sent through the lights. And we need to transform that into a more human-readable format for the analytics that we will do. And also, for the aggregation, we will need to process that information. So we will need to transform the information. And we'll go more into detail later. We'll analyze the information that we have, providing real-time analytics for our customers. So everything that's happening on the system, we want to make it visible for external customers. Then we will aggregate this information, and the reason for the aggregation, basically, and again, we will go more into details later, is that we want to not to create very, very small orders all the time, but we actually want to have meaningful orders. And for this architecture, we will define a daily order. And then at the end of this pipeline, what we will do is deliver this information into the systems or make it available for the systems to consume it. Some other things that we need to consider on the architecture is, one thing, it's the global data. And by global data, I mean this data that will be flowing through the system. We will have data in each one of these components, but we also need to consider this global data on how to manage it. And the other thing within this global data is that we need to understand what's the state of this data. And we spoke before about item potency and how I will know what's the stage of this data so I can replay it if it fails and move it forward through the pipeline. And last but not least, we said that we want to be 100% accurate. And to be 100% accurate, we don't need to just architect the things around that, but also we need to verify it by auditing the information that we're coming with. So we will have the streaming components that are the system is flowing the data from the smart sockets, we collect it, we transform it, we analyze it, and then we stop there for a second. We buffer the information for a day, and after buffering this information, we will move to the batch components, which are aggregation and delivery, and of course, audit. So we spoke up to now about 3 logical entities that we will go through the presentation: data, state, and compute. So now that we have the problem defined, let's start together building this architecture, and we will start with the data part. And specifically, let's start with global data here. So Mike, what options do we have for managing global data in this system?
I think before we talk about picking a solution for our global data, or the data that's going to be shared across our systems, we need to talk about how we're going to manage that data. And first of all of our global data, or all the data that's stored that's going to be used across our systems, must be immutable. And the reason that we do this is for 2 primary reasons. One, auditability, so that we know what actions were performed at any given processing. And secondly, for the replayability that Diego spoke about before. If we need to retry any of our logic, we can just replay it through our system, and we don't have to worry about cleaning up artifacts. The second thing, we need to look at performance bottlenecks that we might get in any solution that we choose. Let's talk about DynamoDB, for instance, where we need to pick a partition and need to worry about the IOPS, or for Amazon's RDS, where we need to worry about I/O. And so we want to monitor these things typically with Amazon's CloudWatch, and set up some alarming thresholds. And the last thing is, of course, security. And everything we do, it's a top priority at Amazon to make sure things are secure. And so we need to have encryption both at rest and in transit. So now when we're trying to talk about the options that we're going to choose, we need to look at structured versus unstructured data. And I want to make sure that we don't confuse formatting with structuring. So formatting is the format that's coming from your upstream systems, like JSON or CSV, some of these common formats that you might get from a file. And that's not really what I'm talking about here. Unstructured data would be that the data store understands the data that you're putting into the store. And so Amazon S3, you could put a file name, and here's my file, but S3 doesn't understand that data at all. It just knows that there's a file, and it has some data enclosed within it. The others would be structured data. And that's if I need to do queries on my data, say, hey, I need the statistic of a data or the state of a data, that would go in a structured data store, like Amazon's DynamoDB, which is a key value store, or into Amazon's RDS, which, if you had relations between some of your data sets, would be a relational store. So Diego, I think it's a time that we look at the data that's coming from our smart sockets and make a decision on what kind of medium we want to use.
Yeah, and that's an important thing. We're always in architecture making trade-offs of things, and that's what we will do during this session too. So here's the data that we're getting presented by the smart sockets. As you can see, it has a JSON format. We have client ID, timestamp, the socket identifier, light identifier. So all this information that is coming, it's coming actually in collections of records. So if you can think each one of the rooms of the hotels, or each one of the different signs will have a collection that will be able to send us this information through. So this is how it looks. And from what you say, this is actually formatted data, right? So if this is formatted data, then we probably want to have it there in this immutable store that can be S3 in this case. And one of the reasons why I would pick S3 here is because beyond that we don't actually need the query ability of this data. We actually want to reduce the cost too. And this will be a lot of data. If you think about any event that happens to any light in all Las Vegas, it will really create millions of records per second. So this is why we want to store it in a place where it's cost-effective and also effective from the speed perspective. So let's choose S3 here on the architecture. And one thing that you said before, and I will get that and use it, is that we said that we want immutable data. And this data will go through different steps. So one thing that we can do, too, is create 3 different S3 buckets. And with that, we can store each one of the stages of this data. Do you think this is a good idea?
Yeah, I think it's time to look kind of at that local store that we were talking about before.
Yeah, and you're right. The local store, it's important because you spoke about the immutability, and if we cannot mutate the records, then how can we process them? So how would the local data look like here?
So we use local data, again, for the mutations of the data. If we need to do some processing, we don't want to process it, obviously, in our local store, or in our global store. We want to take that down to the local store, do our processing, make our mutations, and then move that back to the global store. So our scope of work is limited to the amount of objects that we process in that one run. And so this is where we do our mutations of data. Another reason we'd use a local store is really for caching data, optimizations. And so if you could think about a map that we'd have to change our client identifier to something that's human readable, as Diego spoke about before, we wouldn't want to continuously grab that map from a global store. We'd want to pull that into a local store and then do some checking between, some synchronization between the local store and the global store to make sure that they're in sync. But we get that optimization of only looking locally. And then, again, once we're done with that lifetime of the persistence of that object, or we're doing our mutations, we'll then move it back to our global store and we'll be done. And it's immutable again. So I think we should look at how this local data is transformed in the system that we're designing.
OK, so let's see how this works. We will get the data, and as we transform it, for instance, we will get the client ID that it's like formatted on the own IoT structure into the client ID. And from this cache that you spoke about, we can actually grab the information and transform it through a map to best hotel, for instance, which is the name of this fictitious hotel. We can also transform, we spoke about before about how to aggregate this data daily. If we use the seconds that we're getting from the IoT, we'll get aggregation up to the second. So we want to transform it to a date format also for the use of that aggregation. And then we have the light identifier that can be, for instance, the identifier for the ordering system to make it easier for the ordering system to process these orders. So one of the things that I want to point out here, and it's interesting, is that you mentioned the caching technique. And using that caching actually gives us two more things. One, it's reduction in cost. We're not querying the data store all the time. And the second thing that it gives us is also resiliency against any connectivity issues that we can have to that database. So I think that's good with data, and let's move to the state stage. So how do we deal with the global state? And by global state, I mean how we are tracking the information that is flowing through the system.
Again, we're talking about stores, and you'll see the same stores that we talked about before, and they have, have the same behaviors. So we have a key value store if you need to look something up by a key and get some state associated with that key. Or if you have a relational store where you say, okay, there's states, you could derive a state from two different, there's a relationship between those pieces of state. And then if you just have a blob of state, so I need to grab some file down from S3, and then it has a bunch of state within that file, and then I would move that file as the state changes. And so it really depends on the state that we're looking at and how our system is going to work. So these are the trade-offs or things that we would look at when we're dealing with state. And I think it's important, though, when you're talking about state to really understand the transitions of your state. Are you making the state machine that's overly complicated because you're going to have to deal with all of these state transitions? And really making a map of what of those transitions are is very, very critical when you're dealing with state. And so I think it's a good idea if we take a look at the state machine that we're going to build for this system.
So in this system, we will use a simple state machine. When we receive the information from the smart sockets, remember we receive it in batches of information, we will set it as created. We start the process there, and we know that we received it. And remember that the next stage that we have is transforming this information. So when we are doing the transformation, things can fail. Especially in distributed systems and with these amounts of data, we can actually have a failed state. But the beauty of doing this in an idempotent way is that we can, in any time, replay the same message and actually get to the transform stage again. And from that transform stage, we will analyze it, aggregate it, and set it as complete. So this will be the state machine that we will be using. And based off the options that you gave regarding the different stores that we have, and considering that we have a batch name and a specific state that we want to track, a key value store seems to be like the best option here. What do you think about that?
I think that's right. I mean, you're just tracking state of that batch as it moves through your system. So it's really easy to just say, hey, this is my batch name, as long as you are keeping to those best practices of Dynamo and making sure that you are partitioning properly. OK, so if everyone agrees, we will set DynamoDB as the state machine holder, where we will be able to track the local state, the global state. But then one thing that I also had a question around is that once we have the state there, how does the next component know that it has to pick it up? Yeah, so I mean, especially if we're going to use DynamoDB here, we could do large table scans. And if you can imagine the amount of volume that we'd get from all these lights, it's not really going to be scalable. We'd have to do huge scans and look for filtering on failed state. We wouldn't want to do that. We want to be very explicit in the amount of work that we're going to be doing from our downstream systems. So typically, we could send that data directly to the downstream system. But again, if we talk directly to those downstream systems, we couple those systems together. And typically, in the behavior of two independent systems is they scale differently. And so you've then caused this dependency between the downstream systems and the upstream systems, and you have to protect yourself. And so you'll have some buffer, and you have buffer overrun problems. And so we don't couple systems like that. Typically, we'll take a channel that is in between that can grow elastically. Typically with a queuing system that you could directly share that state, and it has its own explicit amount of work that it needs to get done.
OK, so for queuing systems in AWS, we have Amazon SQS used, or we also have Amazon Kinesis. So what are the trade-offs between those two here?
Yeah, I think we've been going through a lot of trade-offs, and it's really about picking attributes that you need to make trade-offs in. And in this system, we've picked 3 here: ordering, locality, and delivery. And by ordering, I mean, am I going to get those messages in the same order every single time? For locality, is the same logical consumer going to get that message? And for delivery, is there possibilities that I get that same message twice? And so for Amazon's SQS, we are not ordered. It is not localized, and it's at least once delivery, which is very common with a queuing system, a distributed queuing system. And then in Amazon's Kinesis, it's strictly ordered, and it has locality, so the same logical consumer will get that same message. And it's, again, at least once processing.
OK, so we spoke before on the 3 principles for this architecture about item potency. And so then it looks like Kinesis gives us that ability to localize the things and send them through the same set of hosts. If it fails, we can replay the same message, and it will end up in the same place. But one thing that I'm worried about is that you're mentioning here that both of these options have at least one processing, meaning that if I have a record, I know that I will get it, but I might get it duplicated. So how can we deal with that in this case?
So typically, you'd build your own deduplication strategy. If they're not guaranteeing once and only once processing, you have to have some way to deduplicate those messages. And typically, you pick a key that you can say, if I've seen this key before, if I have, then I can deduplicate that particular message out. And if I haven't, then I'll accept that message as valid work. And the nice thing about having locality is we can change the scope of data that we're looking at down to the consumer that's getting that message. And so we don't have to have it across our entire distributed set of workers. We have it just to the consumer that's consuming that queue. So it gains some optimizations there as well.
OK, so that looks like a good idea. Let's use Kinesis, and let me see if I'm understanding correctly. What will happen with Kinesis is that every hotel that is sending me the lights will go to a different partition. So as we get the information from the light sockets, we will move it through the transform, and then it will end up going through this channel for the next stage, which will be the analysis here. But one thing I'm noticing here on this graph is that we probably have hotels that are way larger than others. So how can we actually make the best use of the resources that we have instead of having the hotel 1 going all to one partition and the hotel 2 with a few messages for partition number 2?
I think it's, first of all, we should mention the fact that Kinesis utilizes shards, which are groups of partitions. So if you think that a partition gets hot, they have no way to distribute that load. So you need to be very careful in how many partitions that you're going to choose. And you can do this by adding entropy to the partition that you're selecting, your partition key. And so you'd pick an attribute like hotel identifier as the partition key, and then to add that entropy, you take a hashing function on the entity of work that you're doing, and then modulus the partition key size that you selected. And you can select the partition key size based off of the amount of data that you're getting from that hotel. And it's important that we think about how that's going to change over time, because hotels are going to get larger, some will shut down, and so we want to be able to change those partition key sizes. And so the way that we could do that is by a time versioning on that partition key, where we say at this particular time, based off of a time that's part of that entity. So if you look back at the batches that came with a timestamp, we could use that timestamp to decide which partition key size we're going to use over time. And this really helps us partition our data better.
OK, so that was a little bit complex, so let me see if I understand it correctly. What happens here is that I'm basically adding what you called entropy. I'm adding an extra value to distribute the load between the different partitions here. So that way I can have even partitions. But now, we spoke about being scalable and being horizontally scalable and elastic. So if I think about Kinesis, I think about this stream of shards that I have, and then how can I actually scale up or down based off the needs that I have?
So typically, we do this with like a hotspot manager, something that can understand the data that's coming in and then make changes dynamically. And so we can capture all the I/O statistics coming from our producer, send that to a data store, and then have our hotspot manager read that data, make various changes on the partition keys, and then update that partition key back to the store, and then that gets synced back to the producer. And you do this, again, with a time versioning. The other thing is, I think you mentioned on the shard side, you need to be able to scale up and down your shards. And so the hotspot manager can do that as well. It looks at what the volume across your shards are and make determinations if you need to shrink the amount of shards that you have or grow the amount of shards that you have.
Okay, that actually sounds good. So let's use Kinesis for this. But one thing that I want to reiterate here is that we spoke about some of the techniques for local data to use caching within each one of these components. And to put Kinesis here, we actually need to add these other two things, which are the deduplication logic on each one of the consumers, and also the hotspot management to make sure that we can grow elastically and shrink elastically. So let's go now to the next stage, which is the local state. How do we manage local state?
Yeah, so local state.
Mike, give me a second. I think you copied the same slide from data.
I did. I was optimizing cost.
Okay.
But in reality, it's very similar, right? You're using data stores, key value stores, depending on the use of your data. And so if you take deduplication state, for instance, where you're saying a single consumer can grab that data and look up local state, have I processed this, or have I not processed this? It has that characteristic of what we call worm, write once, read many. I write to my local store that I've processed this data, and I'm consistently reading to say, hey, have I seen this, have I seen this? And then once we're done with our checkpoint, if you think of Kinesis or KCL, where you can say I've done some scope of work, 10 minutes of work, I can then move that store or move that deduplication state back up into my global store or global state store. And then if my consumer dies, it can move to a different host, and I can grab that deduplication state back into that consumer. So we have a nice elastic model, and we have fault tolerance as well.
Okay. So let's review the architecture for a second. We have S3 for the global data. We can store a lot of data at a low cost. We will make that data immutable. We will just change it on this caching on each one of the components. Then we will have the tracking of the state through DynamoDB, and then we will have the Kinesis stream sending the information between the transform and the analyze components. So let's go, now that we have data and state there, let's go to the compute. And tell me, Mike, for the compute, what options do we have here?
Well, we have the new hotness that is serverless compute. So serverless compute, I'm not going to go into details. There's a lot of details in this conference. But basically, we've abstracted away server management. So if you don't want to deal with the server itself, you get out-of-the-box scaling and metrics and logging. And so there's a lot of benefits to moving to a serverless compute. On the other hand, we have the more traditional model, which is has fine-grained controls where we can tweak things depending on our use case. It's time-sensitive. If you have very time-sensitive critical applications that you care about nanoseconds of time, of course, you're going to want to use something more in the traditional model. And then co-location of resources, where if you're using a hybrid approach and you say, OK, I have some set of entities that I know I need to execute on, and I want to execute it seamlessly between the cloud, you'll typically use something like EC2. Also for clustering, as we mentioned here as well, if you have some custom clustering that you're using, you need to know how many specific nodes that you're going to have, and you need to have deterministic behavior there, then the server-based compute is going to be the choice.
OK, so it sounds like for the transform stage, when we are getting all the information, we can use Lambda. As you said, it's the new hotness. I really like things that are easy to manage, and I like things that are trendy, so let's use Lambda there. But then after we are using Kinesis, we spoke about deduplication and about analyzing information. We will need to do more complex operations that are actually merging those different messages that we are getting. So let's use EC2 there. Do you think this is a good idea?
Yeah, I think it's a great idea.
OK, so one thing, if we put Lambda there, it will easily scale. But then the question that I have with EC2 is that we're here in Vegas, and there's all the time new projects coming in, new hotels, new stadiums being built all the time. So how do we scale those EC2 boxes?
There's a very known, well-behaved system that we have, Amazon's EC2 autoscaling, where we determine what the bottleneck is in our system. Let's say we're bound by memory in this use case, because we're keeping that deduplication state, and we have multiple consumers on potentially one EC2 node. We know we're going to be bound by memory, and so we'll set up some alarms that say, hey, we've crossed some threshold, 70% or whatever threshold is determined. And once that alarm goes off, it's being monitored by auto-scaling, and then it'll scale up or scale down your system.
Okay, that's a good idea. So let's add this auto-scaling there with CloudWatch, where we can monitor our resources and scale up or down. So we have the costs under control there too. So let me reiterate, we're getting the information through Lambda. If you can think about the event that is triggered, that transforms directly the information there. It sends it through the Kinesis stream. We have the deduplication, and we also spoke about the hotspot management there. And we move it to this set of hosts that will basically analyze the information and provide visibility to the customers. So how do we do this aggregation? We spoke about batching the information here in this stage. So what do we need to do to aggregate the information here?
Typically, when you have long-running jobs, you're going to utilize something like MapReduce. It's very common. And we have a thing called manifests. Let's the manifests here. And the idea of a manifest is you want to reduce cost when you're talking to one of your stores. And so you would group together work into a manifest, and you pull that manifest down, and it'll let you know the amount of work that you need to do. And so you've really reduced the amount of IOPS hitting each of your stores. And then from that manifest, you'll get a list of batches or a list of work that we said you need to execute on. And then from that, you can then map those records down into a subset of records that you would need for ordering with a single record and a single value.
Okay, so the option in AWS for aggregating records, probably it's EMR. So we can pick EMR. We can use it with Hadoop, with Spark, or any flavor that we want to use here. So let's put this, and as we get the things from EC2, we can use Lambda to push them through EMR. Actually, we can use Lambda to schedule this daily job, or we can actually do it on any pace that we want. We don't need to be constrained up to that, because we have things buffered there, so we can take them as we want. And we're moving it to EMR, and we can set up this EMR cluster. And as I can imagine, Mike, here we're in Vegas. We spoke about these trillions of lights all over, the miles of neon all over. So we'll probably need a huge EMR stack that is standing there waiting for anything that we want to process, so we don't have problems of scale. But do you think that will work?
I really hope we don't design systems like that. We can, it'll work, but we're really underutilizing these huge clusters because we have periodic jobs. Hotels are not the same size, and if we're using just the hotel, this is the data that we need to utilize, we're going to have way more nodes that we need, way more MapReduce tasks, so we want to really optimize that. And we can do that by knowing the amount of backlog that we have or the amount of data that we have, and then making intelligent decisions on managing those clusters. And so if you can imagine a cluster manager that knows the amount of work that's going to be executed, the node times that they're going to be executed, it could stand up and tear down clusters for you before that job execution happens. And so you have this cluster manager that's consistently reading the backlog of work that's going to be executed on, and then it'll stand up clusters, so the bootstrap time, you don't have to pay for that bootstrap time when you're trying to execute your jobs. And then when your jobs actually start, they look at the clusters that are available and say, oh, I can lease this cluster now, utilize and exercise on that cluster, release that cluster, and then it's available for another worker. And because you have the cluster manager consistently looking at the backlog of work, you can also scale up and scale down those clusters. So if they're no longer going to have executions on them, tear them down. We don't need them anymore. Because we really think of them like EC2 nodes, where we have some work, we need to do some work, and then we're done with it. We don't want to pay the cost of running these clusters for a long period of time.
OK, so for now, how this looks is we get the information from the sockets on all these hotels. We get it through Lambda. We put it also in S3 there. We transform it, and we pass it through Kinesis. When we pass it through Kinesis, I want to reiterate the tools that, or the techniques that we are using here, which are the deduplication and the hotspot management. We send it through EC2 with auto scaling that it's already built in then. And when we are using EMR, we are adding this component of cluster management where we can smartly use this as disposable resources. The same thing, as you said, we use for EC2, where we don't care about having that stand up all the time. We can use it, and then we can throw it away and spin up another one whenever we need it. So that gives us a full picture of our processing pipeline. And now we need to actually communicate with the exterior. We need to communicate with the hotels and with the ordering systems that we might have. So what options do we have there for communicating with the external systems?
When we deal with externally facing entities, whether it's another team or it's a different company or your customers, typically we do this in an API format. It's language agnostic, and we can just gather that information and then execute some functions on that. And you want to think about authorization and authentication. Super important because it's not behind your fence anymore. You need to make sure that the clients that are talking to you are your actual light sockets and not some fictitious person ordering 5 million lights for some customer, because that would be a terrible experience. So security is obviously a top priority. The second thing we really want to talk about is scaling, right? Scaling up the amount of nodes that you would need in your back end to handle all these requests. And then optimizations like caching, where if you have somebody across the world, they make the same request over and over, it has to travel all the way across the world to get a request. You want to cache as close to that point of presence. And then the last thing is protection, right? Now that you've coupled systems together because they're talking to you directly, you have to protect yourself against brownouts. And so you do that typically with a throttling mechanism and DDoS protection. And so there's various tools, and there's an extensive list of how to do each of these. And you can piece this all together. You can use a managed framework like Amazon's API Gateway, and it manages a lot of those solutions for you.
OK, so to me, I like simplified solutions, since we spoke about operationally excellence, being operationally excellent. So we basically want to do simple things. It looks like Amazon API Gateway gives us all what we need there, in compound with Lambda, to actually execute the functions that we have there. So that gives us a very good contract there. We will have good contracts with the exterior, good contracts with the downstream systems, and then with these good contracts, we can actually scale up or down internally in our pipeline, and it will be something that will feel completely smooth for these external systems. So now I think we have a good idea of how to get the information through the pipeline up to the ordering system, and we want to do the audits and to validate that. So one thing that we can do for auditing, it's actually replicating exactly the same pipeline that we have here, and then compare the results at the end. So we do a line-by-line comparison, and what happens there is that if I push a code bag, or if any host goes bad and it corrupts the data, I will be able to catch that at the end of the pipeline. Now, the question that I have here, Mike, it's can we simplify that in some way where we don't know we spoke about the next day, right? So I will just know this on the next day if I do that. Can I know this faster?
Yeah, failing fast is critical, right? When you're dealing with especially high volumes, you want to fail as fast as possible. There's possibilities, as you said, there's corruption in your data. And so you don't want that to propagate until all the way at the end when you're getting these results for your billing system. You want to see it before the analytics happen, because your customers are seeing some anomalous data and what's happening, and you're having to do a lot of scrambling to find out what the problem was. And so if you have to wait all the way to the end of the day, that's a terrible experience. So we can do this with incremental auditing, right? Where we say, we have, let's say, a function that says color, take these boxes and color them. And then we can do, as you said, a line-by-line comparison of, did I color these things properly? Yes, great. Our audit passes. We can move on. And then maybe we have a uniqueness function, and it just gets the unique colors. And again, we can do a line-by-line comparison. Did we get the right results? Yes, great. Move on. And because of that transitive property of equality, we can say A equaled B, and B equaled C. Therefore, the whole pipeline is fine.
OK, so basically what you're saying is that when we do each one of these steps, we can actually do line-by-line comparison of what we're getting and get a result and see if we failed, we can fail fast. So for instance, if I push a code back, I can auto roll back, and I don't need to wait to the next day because I will know right away that something is wrong there. And that is great, but we spoke about going from 0 to 100 million records per second. We will have many, many lights here. Is there any way to avoid the costly operation of comparing line by line? Because actually, we don't need that information. The first thing I need to know before anything is if I am right or if I'm wrong.
Yeah, line-by-line comparisons are extremely expensive. You're talking about having to sort and shuffle data and do those comparisons a lot like you would do a MapReduce type operation. And so this is where really checksumming comes in, right? It's a digital identity for a record. And you have to, if you look at the source data and the result data, they're different. It's hard to compare these two results. And so we need to get them into a format that we can do comparisons. And so what we'll do to get a checksum is take a hashing function of our fixed and our transformed values, and then we'll times that by the aggregating value if we're going to do aggregation. And so if you looked at here, when we talk about fixed values, that's values that are static through the entire process. And so as an example, you can see event type, it's outage both on the source set and on the result set. And so these are fixed. Then if we look at transformed fields, those are fields that have changed through the lifetime of the process. So on our source side, we see that client ID has been changed to Best Hotel. Again, that's the human readable. Timestamp has been changed, and light identifier has changed. So we need to, these are our transformed fields. The next thing that we need to do is actually do the transformations and remove anything that is not in our result set. Because these were, as we didn't need that socket identifier for our order. We don't care about that necessarily for the ordering system, but we might care about it when we deliver it so we know which light to replace. And so we do the filtering, we do the transformations, and now our source starts to look a little bit like our result set. And now we need to run our hashing function over both the fixed and transformed fields on both the source and the result set. So you can see here we picked MD5. It's a 1AE, et cetera. Trust me, this is correct. I hope you trust me. And so now we've got an identity for the key, if you will, that we've done in our MapReduce. Now, if we actually move forward, we need to find our aggregating value. And this is the value that in our MapReduce we said this is our value of our key, and this is how we're going to do our aggregations. And then we actually need to perform the multiplication of, hey, we have our hashing identity, times it by the value. And so then we'll get an actual identity for that record. And so if you see here, we have an identity for the source set, which is 1AE. Again, you're timing it by 1, so it's an identity operation. And then on the result set, you timed that identity for the key by 2, and you get a different result. And you can imagine we tried to limit the scale here, but millions of records, right, with all of these different identities.
So let me see if I'm understanding correctly. What you're saying basically is, since we generated this digital identity through the MD5, or it can be any hashing method, we created a unique way of identifying that record. And if we time it by the value that we are aggregating, in reality, adding up these two values, it's the same as multiplying the other value by 2. Is that correct?
Yeah, so if you look at the assertion that we make when we do our audit result, we assert that the sum of the source records are going to be that of the sum of the result set. And then we don't have to do line-by-line comparisons anymore. We can do this rolling aggregation or rolling checksum, and we don't have to sort and shuffle data anymore. We just do an easy computation of a sum.
OK, that makes sense. And let me ask you another question about this. We are trying to build an architecture that is simple enough to, is there a way we can minimize this component and not to create yet another component for this?
Yeah, we can definitely do these in line. And so typically we'd perform whatever operations, and if you think of them as metadata identifiers for that record, you could carry that through your system and just consistently check, hey, did I do the right thing? Did I do the right thing? Did I do the right thing? And you're consistently auditing your data as you're processing it. And so you get a nice quick failure if something was to go wrong, or an intern at 3 a.m. decided to push a code change, and you're like, oh my God, you're not struggling to find out what happened. It just fails, and then we can recover from there or roll back.
OK, that sounds like a good story for auditing. Let me review this architecture together. So we will get information from the smart sockets. We can get as many information as we want through this contract that we defined with the smart sockets. We will get it through API gateway. We will have their authentication, authorization, DDoS control, anything protecting us from the exterior, and also caching of the information. With Lambda, we will be able to actually get these events and transform them as we need, and we spoke about here about the human readable and things for the aggregation, but basically we can do any type of transformation of that individual record. We're persisting this in S3, and as we go along the pipeline, we will do these incremental auditings that are built in line with our processes. And we will use Kinesis as a transport layer with these two techniques that everyone can take home, which is deduplicating the information if we want to make sure that we are doing once and only once processing. And also the spot management or hotspot management, where we can actually see what's going on the charts, see what's going on the partitions, and we can scale up or down the Kinesis stream based off that. Then from there, we will get with Lambda to EMR, where we will use here the growth manager. As we use the growth manager, we will be able to elastically scale up or down also the EMR clusters. And then we will move this information to the delivery part, always keeping the global track of what's going on, and with the capacity of replaying if we need it. So if we see that anything failed, we can replay it again, and it will go through the same process. And another interesting thing there is that we don't have even possibility of duplicates, because if we replay through that deduplication, and since this is idempotent, we're again deduplicating that information. So any possible fail, we're reducing it to basically doing it on the right way. Does that make sense?
Yeah, I mean, we've really reduced our operational footprint here, where at any point in time, if there's a failure, we're safe to rerun, and we don't have to have these really long SOPs about, configure this way, or drop this table, which I hope never happens. And so it's really easy for the operator to hit rerun, and we're good to go. And we don't have to focus on operations all the time. We can focus on the development or the new ideas that we have. And again, there's a lot of implementation details that obviously we didn't cover, we only have an hour. But it's very crucial that we look at our pipelines and we have these best practices, if you will, on both our data, our compute, and then our state.
And in our team specifically, these techniques and these tools, and also the fact that we started moving to manage frameworks that we don't have to be heavily operational when we grow, it allowed us to really focus on the business. And that is something that we all want to achieve in our own companies. We want to focus on the business and not be operating the systems all the time. So I think we did it. Thank you very much, everyone. We will be here for any questions that you might have down the stage. So please spend any time that you want with us to respond to questions. Mike can answer questions. And thank you especially here to Ankit. He's part of our team, and he also helped a lot with the presentation here. So he's also available if you have any other questions. So thank you very much, and please don't forget to complete your evaluations.